So let's start the discussion. Today we will discuss about vector searching and chunking. So basically we have seen some methods to do vector searching, but today we will see how this is actually done for production grade environments, what are the problems and how they are solved in the production grade environment and stuff like this. If you remember some of the discussions from the last week, what we did was we used this idea of comparing each vector with other vectors that are in the entire RAG database, and then we fetch the nearest few documents based on the similarity search. So we discussed this whole mm, sorry, Euclidean distance and cosine similarity, these two methods, and we used to get those nearest neighbors, and then we used to pass them. One problem in this method is, so let's say there are like 1,000 chunks or 1,000 documents, so you will have to do 1,000 searches, right? But what if you have to scale it to 10,000 documents or 1 lakh documents or whatever, 1 million documents? Then as you increase the number of documents, the number of comparisons you have to do goes on increasing. So which means in production grade, if you have huge data that keeps on adding every day or every month, then the process will keep on getting slower and slower because you will have to compare more and more number of points. So you will have to compare more and more number of points, and you have to calculate the cosine similarity or the Euclidean distance between these points to find out the nearest neighbors. So that is the problem basically. So based on 1,000 documents, if you have so much calculation time, the increase in the number of documents increases your calculation time as well. So how do you solve this problem? So there is a smart way for this to solve this problem. It's called navigable small world. So what you do is you pre-calculate the distance between these vectors beforehand. So instead of doing them, so when you have a prompt vector, instead of trying to compare them each with this prompt vector, you create a network, let's say, of comparisons, and then you pre-calculate the distance between each of these vectors, and then you store it as a graph. And what you can do is you can compare to try and find, okay, which one is more nearer to the prompt vector. So let's go through how this is interesting. So let's say you have a query vector whose position comes in this red here, and you need to find which points are nearest, right? To start with, you randomly select one point. So it doesn't have any meaning. You just randomly select, okay, this is the point I will start with. And then what you do is you compute actually what is the distance between these two, and then you compare which one is more nearer to this query vector. So if this point had a certain similarity or a certain Euclidean distance, which of these neighbors is much more nearer and which is farther? So based on this, we figure out that, okay, this point, so from this point, okay, we figure out, okay, this point is much more nearer. Now this point becomes your next candidate for this query vector. And then you follow this process, and then from this point you move to this point, and then from this point you move to this point. So finally you figure out that, okay, at the end, this is the most nearest neighbor, so this is my final return point. So by doing this, you avoid comparing this query vector to all these other black points which were never compared. So you save a lot of comparisons by doing this only nearest neighbor comparisons, because you already had the nearest points pre-computed. So this looks really nice, but one disadvantage is that because your starting candidate was very random, it could turn out that the best candidate might not always be selected, and in some cases it can happen that your path that it traverses actually misses some other point here which was not even connected to this, and somehow this was more nearer. It's quite possible, but okay, it is less. But this is one disadvantage here. Now to optimize this further, there is a strategy that is used called hierarchical navigable small world. So this becomes a really complex word, but okay. Uh, what they do is they create a hierarchy out of it. So imagine you have like 1 million points, right? So this is the innermost layer. So you make layers out of it. This. So you have 1 million layers. So instead of trying to traverse through these 1 million layers to find the nearest neighbor, what you do is you drop certain number of points and you keep like I don't know 1,000 points in the second layer. So this is a lowest layer which has all the points which are pre-computed, and then you drop a lot of these points and keep just 1,000 points here, and you call it a layer 2, which is upper hierarchy. And from these 1,000 points also you drop, let's say, 900 points and you keep just maybe 100 or maybe 50 or 20 points here. And when you start previously, okay, we started, then we follow the same process, right? But what we do is we start with the layer 3, where we randomly select one point and then we find the most nearest point. Let's say you found this point to be the most nearest, and then you jump from layer 3 to layer 2 and you take the same point, and then from this layer you again try to figure out, okay, which one is more nearer here, because now you have more points, right? So let's say you found out that, okay, this point was the actual nearest, and then once you figure out in layer 2, then you jump to the layer 3 and here you do a final optimization. So the advantage is you in the final layer you are already very close to the actual point, because you did all the searches here for all the 50 points, then you got the most nearest, which means that these points here were never relevant, so you never had to do the comparison here. So this doing a hierarchy still saves you from multiple repetitive searches, and is a very smart strategy. And at the end, what you save is you convert this previous problem of having a very linear progression in terms of the calculation time that was needed. Now it becomes very logarithmic, which means that even if you have 1 billion points, now the amount of calculation time needed doesn't increase drastically, because you have this nice hierarchy created. Irrespective of how many sub layers you have, the outer layers have lesser points, which means the amount of calculations at the end you do are substantially less, even if the number of documents you add in your RAG system goes on increasing. So this is the Hierarchical Navigable Small World, or it's called HNSW, which is a very complicated name, but yeah, it seems like kind of latest up-to-date strategy that has been, or that is being used, yeah, to make vector searches here. So this is the strategy.